Hi, welcome to Lecture 5.5, Zeros of Polynomial Functions. Now, in the past, or in past sections, we have already learned what zeros of polynomial functions are. We know that, graphically speaking, when you find what we call the zeros, what you're actually finding are x-intercepts of the function. So these are gotten by plugging in 0 for f of x and solving for the x value. So you're finding where that graph crosses the x-axis. Now, when you have been given at least one zero of the polynomial function and the remainder of it can be factored, we know how to move forward with finding the other zeros. But what if you're given the situation where you have a polynomial, you don't know how to factor it, you haven't been given any of the zeros of the polynomial function so that you can start pulling those out one by one? What do? Well, that's what this particular section is going to cover. So let's go ahead and get moving in it. Okay, so the first thing that we come across in this section is called the Remainder Theorem. And basically all the Remainder Theorem says is that if you divide a polynomial function by some linear factor x minus k, and we've already seen this x minus k come up when we were learning about synthetic division. But if you have these linear factors, x minus k, then once you have divided that out of the polynomial f of x, whatever you're left over with, whatever that remainder polynomial is, or value is what you get when you take the value k. This should remind you of synthetic division, and actually plug it into the function that you began with. In other words, if I take this value k, and in theory, if I want to divide the entire polynomial by that x minus k, to know what remainder I'm going to be left with, all I really have to do is evaluate the function f at k. So we can use synthetic division to actually do that division we're talking about, or we can take the time to plug the value into the function to get the remainder. Now let me remind you that a remainder of 0 means that that x minus k was a factor of the polynomial, and so is the quotient. If we get any other remainder besides 0, then that means that that divisor was not a factor of the polynomial. So let me just show you this. Okay, so let's first begin by evaluating the function by just plugging it in. So we're going to figure out what f of 2 is. In other words, wherever I see x in the polynomial function, I'm going to plug 2 in. So 6 times 2 to the 4th minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7 gives me, okay, so 2 to the 4th is 16, so this is 6 times 16 minus 8. 15 times 4, that's 60. Minus 60 plus 4 minus 7, and I'm going to grab my calculator for 6 times 16. That is 96. Okay, so 96 minus 8 minus 60 plus 4 minus 7. So 96 minus 8 minus 60 plus 4 minus 7 gives me 25. Now, let me show you what the remainder theorem tells us. Let's say we had done this by synthetic division. So I start with my factor x minus 2. So I'm getting that from here. Because remember, x minus 2 equals 0, so x is 2. So 2 is the value that I put on the outside. And I need my coefficients. 6, negative 1, negative 15, 2, and negative 7. Okay, bring down, multiply, next column, combine down, multiply, next column, multiply, combine down, multiply, and 32 and negative 7 make 25. So what we discover here is that whenever you are evaluating a polynomial at a particular x value, that is the same thing. Well, your result is the same thing as the remainder of dividing that linear factor x minus k out of the polynomial itself. And by the way, I can tell in this case, x minus 2 is not a factor because I have a remainder of 25. I need a remainder of 0 to have that as a factor. Okay, so same thing here. Use the remainder theorem to evaluate polynomial at negative 3. I'm just going to use synthetic division now that we know that that's much quicker. So negative 3, have my coefficients 2, negative 3, negative 9, positive 8. I need a 0 there because I've skipped over the x, and 2. And that's going to be my remainder there. Okay, so bring down, multiply, write my result, combine down, multiply, write my result, combine down. Too early to do math in my head. Negative 54, and negative 54 plus 8 is negative 46. 46 and 3 is 138. 138 times negative 3 is negative 414. And that's negative 412. And I'm just going to double check this just to make sure that I haven't made a mistake with my calculations this morning. Like I said, it's early, so smart to double check, at least in these first stages of working through this. Okay, so I'm just going to put this into my calculator. Negative 3 to the 5th power is negative 243 times 2. Okay, so this is negative 486. And let's see, negative 3 to the 4th is negative 81 times negative 3 is positive 243. Negative 3 cubed is negative 27 times negative 9 is positive 243. And negative 3 squared is negative 9 times 8 is negative 72 plus 2. positive 243. Okay, so negative 486 plus 243 plus 243 minus 72 plus 2. Yeah, I figured I'd made a mistake somewhere in my work. Let me find my mistake up here. I ended up getting negative 70 here. Let's see what's going on. Let me double check my work. This just goes to show math is all about persistence. It's about estimating, double checking yourself when you can, and not giving up. Okay, so I brought down my 2. Let me just make sure I have my coefficients correct. X at negative 3, 2, negative 3, negative 9, 8, 0, and 2. Okay, so I brought down, I multiplied 2 times 3 and got negative 6, combined down and got negative 9. Negative 9 times negative 3 is positive 27, and 27 minus 9 is 18. 18 times negative 3 is negative 54. Negative 54 plus 8 is negative 46. Negative 46 times negative 3 is 138. And 138 times negative 3 is negative 414. Okay, so maybe it was the checking that I made the mistake in. Let me do this again. Negative 3 to the 5th power is negative 243 times 2 is negative 486. Negative 3 to the 4th is negative 81 times negative 3 is positive 243. Negative 3 to the 3rd is negative 27 times negative 9 is positive 243. Negative 3 squared is negative 9 times 8 is negative 72, and then that's plus 2. All right, something's up here. Negative 486 plus 243 plus 243 minus 72 plus 2. I'm getting negative 70 again. Something ain't right. Okay, for the sake of time, we'll move forward, and I'll do a special video just on this problem because for some reason I can't figure it out. I don't know why I'm getting different numbers here, and I've got to figure out where I've made my mistake. But let's move forward. That's the process. Okay, according to the factor theorem, k, so that value from x minus k, is a 0 of f of x if and only if x minus k is a factor of f of x. We already know that. We can use synthetic division to divide the polynomial by x minus k, confirm that the remainder is 0. Then we can use that fact of the remainder of 0 to rewrite the polynomial as a product of x minus k and whatever you had as your quadratic quotient. Well, it says quadratic because it's talking about 3rd degree polynomials, but it's whatever quotient is left over there, whether it's quadratic or not. If possible, factor the quadratic, write the polynomial as a product of factors. Okay, so we start out with a factor of x plus 2, and it says to show that that factor is a factor of x cubed minus 6x squared minus x plus 30. Find the remaining factors, use the factors to determine the zeros of the polynomial. Okay, so our polynomial f of x. We first need to determine if x plus 2 is a factor. And remember that's x plus 2 equals 0. So x is negative 2. So k is negative 2 in this case. And I'm going to run it through. 1, negative 6, negative 1, and 30. And I haven't skipped over anything, so bring down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, and I get a 0 remainder. So here's what I know so far. I know that x plus 2 is a factor, and I have gone down in degree by 1 for my quotient, so that is x squared minus 8x plus 15. So I also know, since I had a remainder of 0, that x squared minus 8x plus 15 is also a factor. But we want to get all the way down to the zeros, so I want to factor my quadratic. Okay, so to get the 0, 0 equals x squared minus 8x plus 15. I'm not going to go through the factoring process here because I can do this one in my head. There are other videos where I have walked through the AC method. This ends up being x minus 3 times x minus 5. Okay, so here's what I know now. I know that f of x, my original polynomial, is equal to x plus 2 times x minus 3 times x minus 5. So now I just have to use the zero product property to find all the zeros of the polynomial. And that's the easy part. X plus 2 equals 0, x minus 3 equals 0, x minus 5 equals 0. Here, x is negative 2, x is 3, x is 5. So, oh, I just thought about another way we can look at that last problem. Sorry, I'm obsessing. Let's go back one screen. Let me write down my potential remainders here to see which one's correct, to see which one I made my mistake in. Okay, so and f of negative 3, and that is for the polynomial 2x to the 5th. This is good to see, actually. I'm glad I made this mistake because this is going to give you another avenue to check and see where you may have gone wrong with something. Okay, so one time I got a remainder of negative 412, and another time I got a remainder of negative 70. 2x to the 5th minus 3x to the 4th minus 9x cubed plus 8x squared plus 2. Let's go look at our online graphing calculator at desmos.com. I'm just getting my screen ready with the calculator on it, and then I'll take you out to my screen. Okay. So this is a way that you can check and see if you have found the correct value for the remainder. Because if it's the same thing that you get when you evaluate the polynomial at that particular k value, that's what you're going to get when you plug into the function as your output value on your graph. So we'll just go check it out. Okay, so I'm just going to put the function on here, 2x to the 5th minus 3x to the 4th minus 9x cubed plus 8x squared plus 2. Okay, let me hide this and this so we get a big picture of our graph. And I need to zoom out a little bit because I want to know what I get when I plug in -3. Let me get on my graph here. I'm at -1, and I'm going to have to zoom out a lot. Get way down there. Well, let me see if the -70 is correct first before I go too far. Okay. So I'm at -2. Looks like it's going to be the -400. So I've made my mistake in actually evaluating. Let's see what we get at -412. See if it's 3. Yeah, it's the -412 one that's correct. Okay, so watch this. Right at negative, let me see if I can get it exactly -3. I don't know if it'll let me. Yep, -3, -412. So we did our synthetic division correctly, but apparently I can't multiply and add this morning. So, but there's another way to check. It has to be compatible with the algebra you've done or the calculation that you've done, because it literally is what you get out of the function when you plug that value in. That's what you're doing when you're evaluating functions, is you're putting that input value in and seeing what you get out. Hopefully that was helpful. Like I said, I guess it's good that I can't multiply and add this morning. Okay, so I've made some mistake in here somewhere, so we'll just scratch that. Okay, let's do this again. Same type of problem. We're using the factor theorem to find the zeros, and we're given that we have a polynomial, that we have a linear factor of x minus 2. So a factor of x minus 2 is a k value of +2. One, 4, -4, -16. Okay, combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, and I have a 0 remainder, which so far this tells me that f of x is equal to, I have my factor of x minus 2, and then I have my leftover factor of x squared plus 6x plus 8. Okay, once again, I can factor this in my head. So f of x is equal to, I have that first factor of x minus 2, and I know that's a factor because I have a remainder of 0. And then my x squared plus 6x plus 8 factors as x plus 2, x plus 4. Using my zero product property, x minus 2 equals 0, x plus 2 equals 0, x plus 4 equals 0. Here x is 2, x is -2, and x is -4. Okay, using the rational zero theorem to find rational zeros. The rational zero theorem can be a little bit confusing at first, but it's really not that bad. So to see where the rational zero theorem comes from, we're going to take a look at this example in the center of the page. What it tells us is that when you have a polynomial, right here, the only possible zeros, well, rational zeros. The only possible rational zeros come in the form, now these are possible rational zeros. They're not exactly rational zeros. We have to check and find out. But the only possibilities you can have come in the form P over Q. P is any factor of the constant term, which is the last, just the number term on the end. And Q is a factor of the leading coefficient A sub n. So if I'm given this polynomial right here, if I want to list out all possible factors that, or I'm sorry, all possible values that could be zeros of the polynomial, I do P over Q. P are factors of A sub 0, your constant. Q are factors of A sub n. So if I list out all the factors of A sub 0, in this case A sub 0 is 6. So that's positive negative 1, positive negative 2, positive negative 3, positive negative 6. I also have all of the factors of A sub n, which is 20 in this case. Those possibilities are positive negative 1, positive negative 2, positive negative 5, positive negative, oops, I forgot 4, positive negative 10, positive negative 20. So I actually do the division to list out all of the possibilities. I'm not going to list all these out, but you end up getting all the integers, positive negative 1, 2, 3, and 6. Then you have to go back and divide. So when I'm dividing by positive or negative 1, those just give me the integers in the numerator anyway. But I could have positive negative 1/2, positive negative 1/5, positive negative 1/4, positive negative. So it just narrows your possibilities down from infinite to here are the only the possibilities for the rational zeros. And it can be anywhere from 2 that show up to 20 that show up, but it's not infinite. So we know that when we have the linear factors, or our polynomial is factored, when we multiply the first two terms together, those are going to create the first term. And when we multiply the last two terms together, that's going to create the last term. So that's why we use the coefficients of the constant term, A sub 0, and the factors of the leading coefficient, A sub n, to determine what these values are that we're looking for. And you can see how it goes together in this particular polynomial. Okay, so let's work with this. All right, so given the polynomial function f of x, you use the rational zero theorem to find rational zeros. Determine all the factors of the constant term and all the factors of the leading coefficient. Then you put those into that P over Q and determine what your positive and negative candidates are. And then you actually find those. I use synthetic division. They're telling you to plug it into the function, but we know that it's the same exact thing. So what we do is we just start using our possible rational zeros as our k values with synthetic division, and we reject any that have a remainder that is not 0. If it's a remainder of 0, then you found yourself a factor there. Okay, so let's just list all possible factors for this first function. 2x to the 4th minus 5x cubed plus x squared minus 4. in this case, okay, so we're basically trying to do P over Q. So our p-value are the factors of a sub 0, and in this case, a sub 0 is -4. Q are the factors of a sub n, and in this case, that is 2. Okay, so all the factors of -4, well, we have positive -1, positive -2, positive -4. All the factors of 2 is positive -1, positive -2. Okay, so each of these factors in the numerator divided by positive or -1 just give us the integers in the numerator. Positive -1, positive -2, positive -4. All right, now we have to think about, okay, well, what happens when we do the division here? So that first one gives us the possibilities of positive or -1/2. And then we move to the 2 over 2. Well, that's just 1, so we've already got positive and -1 covered. And then we move to the 4, and 4 over 2 is just 2, so that's positive -2. We've already got that covered. These are the only possibilities. These 8 values are the only possibilities for the rational zeros of that function. Okay, so let's take it all the way through in this next one, finding the rational zeros. So the first thing we want to do is figure out what our possibilities are, P over Q. So my p-value is 1, or my a sub 0 value is 1, so the only factors of 1 are positive or -1. And my a sub n value is 2, so the factors of 2 are positive -1, positive -2, which gives me the possibilities of positive -1 and positive -1/2. Now we start the trial and error process. So I'm going to start with positive 1. Don't forget this is a factor of x minus 1 there that we're checking. And here's a nickel's worth of free advice when you're doing this. You want to try it until it fails. The reason you want to try a value until it fails is because it may be in there more than one time. We know that there are factors that have a multiplicity higher than 1. That determines how it approaches and crosses the x-axis. So it may be in there twice, it may be in there 3 times, or whatever. You got to keep on trying it until it fails. Okay. So we have 2, 1, -4, 1. Bring down, multiply, combine down, multiply, combine down, multiply, combine down. So we found the factor. Here's what we know so far. We know that f of x is equal to x minus 1. There's one of our factors. However, I need to see if it's in there more than one time. So what I'm going to do is drop another house down and just use the quotient polynomial to test 1 again to see if it's still in there. So bring down, multiply, combine down, multiply, combine down. This time I have a remainder of 4. So what that means is this one fails. It's only a factor one time. So now I take the remaining quotient polynomial. So at this point, I know that I have 2x squared plus 3x minus 1. And I can continue my synthetic division process on this leftover polynomial, this quotient polynomial. So this time, I'm going to test x plus 1, and that will be a negative 1k value, and I'm going to use the coefficients of my quotient polynomial. See if I can continue pulling out. Bring down, multiply, combine down, multiply, combine down. Okay, so I have a remainder, no go here. Now I'm going to move to 1/2. Okay, so positive 1/2. And I have coefficients 2, 3, negative 1. Combine down, multiply, write my result, combine down, multiply, write my result, combine down. I have a remainder, no go. So I'm finally going to test negative 1/2. 2, 3, negative 1. Bring down, multiply, write my result, combine down, multiply, write my result, and combine down, I get a negative 2, no go. I only have one rational 0, and the only rational 0 I have comes from x minus 1 equals 0, so this thing is only going to cross the x-axis one time at a value of 1. Let's go double check our work with the graphing calculator. So let me write down this equation, 2x cubed plus x squared minus 4x plus 1. Okay, I'm going to go out to my graphing calculator. It's going the wrong way. I need to be zooming in, and I was zooming out. Okay, and let me open this up. And we have 2x cubed plus x squared minus 4x, plus 1. Once again, I've made a mistake. I think I need to quit recording 7 a.m. lectures because I have more, rational 0. These might not be rational. I might be getting upset for no reason. Okay. So we definitely have the 1 showing up, and we found that one. Now let's check these other 2. Okay, that's not a rational number. That is a value that was an irrational number, so the decimal is not repeating and it didn't end, that's rounded. And then we have another irrational 0. So remember, this is the rational 0 theorem. So we only have one real rational 0. Phew! I was worried I had made another mistake in front of y'all. I wasn't worried too much, but I was worried. All right. Okay, same thing here. Let's take it through the process. So let's start by identifying what our possibilities are with P over Q. So the factors of a sub 0, which is 1, so positive, negative 1, over the factors of a sub n, which is just positive, negative 1. The only possibilities here are either positive or negative 1. This is an easy one. Okay, let's check positive 1. Remember, this is an x minus 1 factor. So 1, negative 5, 2, positive 1. combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, combine down, no go. Okay, so let's check an x plus 1, that is an k value of -1. 1, -5, 2, 1. Combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, combine down. I am showing no rational zeros, so let's definitely go take a look at this graph. Remember, no rational zeros. We could have irrational zeros that show up. So x cubed minus 5x squared plus 2x plus 1. Okay. X cubed minus 5x squared plus 2x plus 1. Okay, let's see if any of these are rational. Irrational, irrational, and irrational. So no rational zeros. So you can tell we're going to have to do some work to figure out, okay, well, what are those irrational zeros? We have that left to go. Okay, so the rational zero theorem helps us narrow down the list of possible rational zeros for a polynomial function. Once we have done this, we can use synthetic division repeatedly to determine all of the zeros of the polynomial function. Okay, so this is actually where they introduce in the section what we were just doing. We were cheating and using synthetic division because it's quicker than plugging in our x value into the function. Okay. P over Q. Positive, -1. Positive, -1, positive, -2, positive, -4. Okay? So we have the possibilities of positive, -1, positive, -1/2, and positive, -1/4. We'll start with positive 1, which is x minus 1. Okay, look, we've skipped over our x squared term. So we have 4 0x squares, -3x's, and -1. Combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, and we have a winner. So far, let me color code this. We have an x minus 1. So far, we know that f of x has a factor of x minus 1. We need to check and see if it's in there again. So I'm going to drop down. I'm going to test 1 again. Combine down, multiply, write my result. Combine down, multiply, write my result. Combine down. Okay, so it's only in there once. And I have my quotient coefficients as 4, 4, 1. So this is 4x squared. So we started with a cubic, took a factor of x out. 4x squared plus 4x plus 1. Okay, now we need to check and see if -1 is in there. So for a factor of x plus 1, we need to check -1. And we only need to check it in our quotient polynomial. So 4, 4, 1. combine down, multiply, write my result, combine down, multiply, write my result, combine down. I have a remainder of 1, no go. Okay, now I need to check 1/2. So this is x minus 1/2. And I'm checking 4, 4, 1. Combine down, multiply, write my result, combine down, multiply, write my result, combine down, no go. Now I'm going to check negative 1/2. Okay, 4, 4, 1. Combine down, multiply, write my result. Combine down, multiply, write my result. We have a winner. Okay, so this was a factor of x plus 1/2. So, let me color code. Now I know that my f of x is equal to the first factor of x minus 1. Then I have an x plus 1/2, and what I'm left over with is a 4x plus 2. So I've gotten all of my factors, and they ask to find a 0, so we have to apply the 0 product property. So x minus 1 equals 0, x is 1. Then we have x plus 1/2 is 0, so x is negative 1/2. And then finally, 4x plus 2 equals 0, subtract 2, 4x equals negative 2, divide by 4, and I get x is negative 1/2. It was in there twice. So I have 2 rational zeros. This one has a multiplicity of 1, so it completely crosses. This one has a multiplicity of 2, so it touches and turns. And we could go look at that. Let me write it down. 4x cubed minus 3x minus 1. Let's go take a look. Four x cubed minus 3x minus 1. Okay, so we had a touch and turn at negative 1/2, and we have a completely cross at 1, which is exactly what we were suspecting. Nice. Okay, same thing here. Oh, that's the same problem. I forgot I gave myself extra room. I didn't think I was going to have the room to work in on the last page, but I did. Okay, the fundamental theorem of algebra. Sounds scary, doesn't it? It's not that bad, though. Fundamental theorem of algebra says that if you start out with a polynomial of degree n, f of x of degree n where n is greater than 0, f of x has at least one complex 0. Okay, so we can use this theorem to argue that if f of x is a degree of polynomial n, and a is the coefficient, a is a non-zero real number, then f of x has n, that's the degree, linear factors. These are linear factors that we've been looking at the whole time. And it says where C1, C2 through Cn are complex numbers. Therefore, f of x has n roots if we allow for multiplicity. So this is just basically saying that whatever the degree of your polynomial is, that is how many linear factors you're going to have that make up that polynomial. Now, they don't all show up as real zeros. Some of them are complex. But you're going to have n linear factors, no matter if they're real or complex numbers. Does every polynomial have at least one imaginary zero? No. Some of them have all real zeros. So, don't always expect to have a complex zero. Well, I take that back. A complex number is not necessarily imaginary, so, but don't expect to always have an imaginary zero. Okay, so find the zeros of f of x. We're taking it through the entire process from beginning to end. So let's determine P over Q so we can narrow our field down from infinite to a few possibilities. The factors of 3 are positive, negative 1, positive, negative 3. And the factors of 3 are positive, negative 1, positive, negative 3. So we have the possibilities of positive, negative 1, positive, negative 3, and we have to get that 1/3, positive, negative 1/3. Okay. So let's start testing. We'll give ourselves to write our room to write our results. F of x is equal to. So I'm going to start testing with positive 1, which is an x minus 1. Okay, so 3, 9, 1, 3. Make this a little smaller. Okay, combine down, multiply, write my result. Combine down, multiply, write my result. Combine down, multiply, write my result. Combine down, no go. Now let's check x plus 1, which is a negative 1, k value. 3, 9, 1, 3, combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, combine down, no go. Now let's check an x minus 3. That's 3, 9, 1, 3. Combine down, multiply, write my result, combine down, multiply, and I can't do 18 times 3 in my head, 54. Write my result, combine down, multiply, write my result, combine down, no go. All right, let's test an x plus 3, which is a negative 3 k value. Okay, combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result. Of course, this would be a winner, and I'm at the bottom, so I don't have room to continue doing my synthetic division to check it again. So I am going to take a picture of this, and I'm going to write an arrow here that shows you I'm moving up here to do this. Let me paste it. Okay. And stick it to the board. Okay. All right. I'm going to check it again to see if it may be in there again. Remember, we have multiplicity to think about. So far, I know that x plus 3 is in there at least once. I'm going to drop another house down. I'm checking -3 again. Combine down, multiply, write my result, combine down, multiply, write my result, combine down, no go. So it's only in there once. Here's what I know so far. Now I've got to check 1/3 and -1/3. So I'm going to check 1/3, which is x minus 1/3. So 1/3. I can use my quotient values, which are right here. So 3, oops, I grabbed a white pen. 3, 0, and 1. Combine down, multiply, write my result, combine down, multiply, write my result, and combine down. 3/3 plus 1/3 is 4/3. Either way, it's got a remainder, so it's a no-go. I still need to check x plus 1/3, so that is a -1/3 factor. K value. Oops, I was about to write K instead of 1. Okay. Combine down, multiply, write my result, combine down, multiply, write my result, combine down, I still get 4/3, no go. So I have one rational theorem. However, I'm left with a 3x squared plus 1. And it said find all the zeros. So I have 1 0 here. X plus 3 equals 0. X is 3. I have potential imaginary zeros here. 3x squared plus 1 equals 0. Subtract 1. 3x squared equal to -1. Take the square root. Or no, let me divide that 3 off first. Divide both sides by 3. X squared is -1/3. Take the square root of both sides. I get that x is equal to positive or negative square root of -1/3, which is positive or negative I square root of 1/3. So this is actually 2 different zeros here. I end up with 3 zeros. So if I'm listing them out, my zeros equal 3. I have I square root 1/3 and negative I square root 1/3. Notice you had a degree of 3. My n was 3, and I've got 3 zeros. It doesn't mean that they're all going to be real, but you will have as many zeros as the degree of the polynomial, and that could be a mixture of real and imaginary. Okay, let's do it again. So we have P over Q. P is positive -1, positive -2, positive -4. Q, positive -1, positive -2. So we've got all of our integers, positive -1, positive -2, positive -4. And then we have 1/2. Positive -1/2. All right, we start the process. So x minus 1, 2, 5, -11, and 4. combine down, multiply, write my result, combine down, multiply, write my result, combine down, multiply, write my result, combine down. We have a winner. So this is an x minus 1. We know it's in there at least one time. We're going to check and see if it's in there multiple times. So I know that I have at least one factor of x minus 1. All right, I'm going to check again by dropping down and checking 1 again. 2, multiply, write my result, combine down, multiply, write my result, combine down, no go. So at this point, I have a leftover quotient of 2x squared plus 7x minus 4. Now, I usually don't continue with the synthetic division process once I've whittled something down to a quadratic. Because if I run this through the quadratic formula, that's going to give me my zeros, my x values. So if I use the quadratic formula to solve 0 equals 2x squared plus 7x minus 4, then I am finding those other two zeros. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Negative 7 plus or minus the square root of 49 plus, let's see, that is 16 times 2, which is 32. 49 plus 32 is 81. Oops, that's a 4. Okay, so this is negative 7 plus or minus the square root of 81 over 4, which is negative 7 plus or minus 9 over 4. So we have a plus and a minus. We have negative 7 plus 9 over 4, negative 7 minus 9 over 4. Negative 7 plus 9 over 4 is 2 over 4, which is 1/2. Showed up as a possibility. And negative 7 minus 9 is negative 16 over 4, which is negative 4. Also showed up as a possibility. So from this quadratic, I get two x-intercepts, and they're both real, of 1/2 and negative 4. And from my first work, x minus 1 equals 0, x is 1. So this thing crosses the x-axis at 3 real zeros. Real rational zeros at that. So let's take a look. Let me write it down. So 2x cubed plus 5x squared minus 11x plus 4. Two x cubed plus 5x squared minus 11x plus 4. Okay, so we have a real 0 at 1/2 and a real 0 at 1. We found one at 4 too, didn't we? Let me look. Let's go back to our negative 4. Maybe I just wasn't looking far enough negative. Let's see. Let's go back to our graph. Yep, I bet that's it. And let me close this and zoom out a little bit. And there we go. negative 4. Right there. 3 real rational zeros. Nice. Okay, so use the linear factorization theorem to find polynomials. So we're working backwards. We're going to be given zeros. We know that if we have a complex zero that is imaginary, we have its opposite that shows up as well. Because you have to add and subtract the square root in the quadratic formula, which is what we just did a moment ago. So you're always going to have complex conjugates show up. In other words, if you have a zero in the form of a plus bi, which is really x minus a plus bi, you will always have its complex conjugate, which is a minus bi or x minus a minus bi. So you always, whenever you have an imaginary zero show up, its complex conjugate will always show up. This is called the complex conjugate theorem. Okay, so we are told to find a 4th degree polynomial. That means n is 4. I'm looking to write 4 linear factors with real coefficients. It has these zeros, negative 3, 2, and I. And this is going to help us find our a value. We know that f of negative 2 is 100. So here's what we know so far. We know our polynomial. We have a real, and by the way, we know all these factors are in the form of x minus c, or our earlier sections called it x minus k. Some constant value. These are called linear factors because they're linear. X is raised to the understood first power. So what we know from this information right here is that we have an x minus negative 3 factor, we have an x minus 2, and we're told we have an x minus I. But what we just learned was that whenever you have an imaginary factor show up, its complex conjugate will always show up, x plus I. There are our 4 linear factors. Now it wants us to write the polynomial, not in factored form, so we've got to do all this multiplication. So the first thing I'm going to do is rewrite x minus negative 3 as x plus 3. I'm going to multiply that by x minus 2. I'm going to multiply my x minus I times my x plus I, and then I'm going to multiply those two together. Lots of multiplication here. Let me show you the multiplication that I will be doing. I'll go here and here, here and here. I will also go here, 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 and here. And I'll keep this first line color-coded for you. Okay, so I'm going to do my magenta. X times x is x squared. X times negative 2 is negative 2x. 3 times x is positive 3x, and 3 times negative 2 is negative 6. Okay, moving to my complex conjugate. X times x is positive x squared. X times I is positive xi. Negative I times x is negative xi. And negative I times positive I is negative I squared. However, what we know about I squared is that I squared is negative 1. So that's negative negative 1, which is just a plus 1 there. So this whole thing right here is just a plus 1 because it's negative negative 1. Okay. Putting together like terms. I have an x squared here and an x squared here. That's 2x squared. I have a negative 2x and a positive 3x, which is a positive x. My xi and negative xi drop out because they make a 0. They're a 0 pair. So I just have a plus x. And then I have a negative 6 and a positive 1, which leaves me a negative 5. I think I got everything. Yep. Okay, so there's the possibility that I had a scale factor, that a factor pulled out. So what I now need to do is recognize that I could have some a factor out in front that was a GCF of this polynomial. To figure that out, I use the fact that when I plug in negative 2 for x, I get out 100. So I get out 100 if I plug in negative 2 for x. So this is 100 equals a times 2 times negative 2 squared. Negative 2 squared is 4. 4 times 2 is 8. Minus 2 minus 5. So 100 equals, okay, 8 minus 2 is 6. 6 minus 5 is 1. So that is 1 times a. So a is 100. All right, so here's what I know. f of x is equal to 100 times that polynomial I found, 2x squared plus x minus 5. And when I distribute, I get my final polynomial of f of x equals 200x squared plus 100x minus 500. And that's it. That's all I have for you. I hope this was helpful.